Hey guys, today we're going to go over how to do the LeetCode medium called validate binary search tree. So we get given a root of a binary tree and we want to determine whether it is a valid binary search tree. So in a binary search tree, the left subtree contains only nodes with keys that are less than the node's key, and the right subtree contains only nodes that are greater than the node's key, right? So with that being said, we look at the function that's get given to us, which is bool is valid bst, and it takes in a root. However, we can't actually just use this function to solve this problem because we need a max and a minimum to compare our root's value to. In that case, we would create a helper function. So we could name the helper function bst helper, which passes in a root, a minimum, and a maximum value. So you might wonder why we are using long min and long max instead of int min and int max, and the reason for this is integers are 32 bits, whereas longs can be 32 bits or 64 bits depending on the system. With longs being 64 bits, it can hold integer values that are much higher than ints can. So we define our BST helper, right? And we take in a node, we take in a minimum value, and we take in a max value. And we need our base case, so we put it inside an if statement. We check if node is equal to null, and we return true. This will be our base case. Next, we want to double check if it breaks the condition of a binary search tree. So we need to check whether the value of the node is less than the minimum value given, or the value of the node is bigger than the maximum value given. Notice how we have equal signs. So if it's equal, it's also considered wrong because it needs to be smaller or bigger. Therefore, we return false for these conditions. And now we call the helper function recursively. So we return BST helper, we call the nodes to its left, and we don't change the minimum value, but we do change the maximum value. The reason why we change the maximum value is because we want to make sure that all of the left subtrees are smaller than this one, and we recursively call it on the right subtree as well. This time we change the minimum value because all of the right subtrees have to be greater than this minimum value, and we don't change the max value. So if we run this, it works, and then we can submit it and see how we do. Great, so we beat 96% and 81%. Awesome.